In this video, we will explore how the midpoint of 2 points can be obtained using a compass and straightedge in plane geometry. Even though the problem seems straightforward, it is important because it sheds light on critical concepts in mathematics, such as the Archimedean property and the building blocks of calculus, namely infinitesimals and the construction of real numbers. In the Elements, Euclid introduces 5 postulates after providing definitions of different geometric objects, such as points, lines, straight lines, and their relationships. Here, we should point out that the technical distinction between a line and a straight line, along with many other issues, has led to a historical debate regarding the originality of the versions of the Elements used in the modern era. However, we will ignore these historical aspects and take the Elements as they are. The first 3 postulates of Euclid are important in this context because they discuss the relationships between points, lines, and circles. Before getting into the details, it would be beneficial to understand these relationships better. First, let us look at how Euclid defined a point, a line, and a circle. Euclid begins Elements with definitions of a point, a line, and a surface. The definition of a point is given first. The definition of a straight line comes later and relies on the definitions of a line and a surface. Probably from a purely mathematical point of view, he starts with the definition of a point. We say probably because, as we read on, we understand that he defines a point by what it lacks, such as length and width, attributes that are later introduced in the text. This is understandable, since at that time a 3-dimensional perception of the world was the essence of physical reality, so everyone took it for granted. So here we will adopt Euclid's approach and first introduce the objects that possess these attributes to clarify the idea. Still, with our 3-dimensional perception of physical reality, we would have difficulty imagining objects that have only length and width, but no depth. So, from Euclid's perspective, a point is a mathematical construct that has no part. Now, it's pretty ironic to try and describe something that has no attributes whatsoever. This is likely why later English translations of the Elements introduce the concept of position to help us understand. Essentially, a point in Euclidean geometry isn't really an object, it's a location, a marker in space. But since we can't visualize something with no size that's also visible, we just use a dot on the screen with a label to represent that position. But one of the most fascinating attempts to convey this abstract idea comes from Oliver Byrne in his 1847 edition. Byrne used a brilliant system of colors to illustrate the concepts in the Elements. And for the point, he offers this incredible analogy. He says, imagine 3 colors meeting on a page. The exact spot where they converge isn't blue, it isn't yellow, and it isn't red. It occupies no area of the paper itself. If it did, it would belong to one of the colors. Yet, this junction exists. It has a definite position, but no magnitude. So, with a little thought, this meeting of 3 colors gives you a perfect idea of a mathematical point.
Similarly, a line is defined as a breadthless length according to definition 2. For the time being, let us skip definitions 3 and 4 and jump directly to definition 5 in order to complete the fundamental abstractions. With this reasoning, Euclid defines a surface to be a construct that has only length and breadth. It is interesting to emphasize once more that none of the concepts introduced by Euclid in the first 5 definitions can be observed in our daily experience of physical reality. We cannot see a point, we cannot see a line, and we cannot see a surface as defined by Euclid in our world. They are pure mathematical or geometrical abstractions. Here is a crucial point. Euclid actually axiomatizes the line by relying on another extremely important concept in mathematics, length, in his original wording, or in our contemporary understanding, distance. An extension of this idea constructs the surface, which we now understand relies on the concept of area. Therefore, Euclid is inherently discussing multiple points, markers, or positions, as well as their configurations, which are described by a form of measurement like length or width. So, if you have a single point in Euclidean space, there is nothing interesting to talk about. If you have two different points, then Euclid claims that besides having two distinct markers, these 2 points together automatically yield a fundamental attribute, the distance between them, which is the concern of definition 2. So definition 2 focuses on a kind of measuring stick that will be used in subsequent constructions. Again, we should keep in mind that, like a point, a line in the elements is only a construct or a tool. In definition 3, Euclid explicitly has the first two constructs, namely point and line, interact with each other, and states that if we want to make any measurement with our measuring tool, we need two different points. In the next step, Euclid probably thinks about what happens if a third point comes into the picture. Based on what we have said up until definition 3, when we have three different points, we can define three pairwise distances. Among the infinite possible configurations of these points, one stands out as uniquely simple, the straight line, or, in modern terms, a line segment. The straight line is exceptional because it remains fully describable using only its two endpoints, even when additional points lie between them. In other words, the straight line is the minimal geometric object that satisfies the conditions of the first definitions simultaneously. It represents the simplest possible extension of Euclid's foundational constructs while preserving their core principles. Finally, Euclid can comfortably introduce the circle based on the two-point construct, which includes not just three but infinitely many points. A circle is, technically, the set of points whose distance from a fixed center point is equal to a given length. This given length can be defined by the distance between the center and any point on the circle's circumference, elegantly extending the two-point distance concept to an infinite collection of points.
After this long introduction, we can go back to our problem of finding the midpoint of two given points using a compass and a straightedge. At this point, we need to emphasize that we will use both the straightedge and the compass. However, once we decide on a certain separation between the legs of our compass, we will not change it until we locate the midpoint. In other words, all the circles to be drawn will be of the same size. We adopt this constraint because the problem is more interesting in this form due to the symmetries, generalizations, and algorithmic structures we will encounter throughout our journey. We will come back to that point again later on. Now, assume that we are given 2 points on a flat surface. First, we need to identify where the midpoint is located. As discussed in Euclid's elements definitions and postulates, the midpoint should lie on the straight line segment that joins the two given points. So the midpoint should exist. However, because we can only use a straightedge, which draws a straight line, but cannot measure any distance, we need to locate the midpoint exactly on this line using only the compass. Of course, the first question that arises is, how wide should the compass legs be separated in order to locate the midpoint? This question can be answered in many ways, and each answer leads to different outcomes. Let us examine these different approaches one by one. First, let us assume that the compass legs are separated in such a way that when one of the points is taken as the center of the circle to be drawn, both points are contained within the circle. In other words, the compass legs are separated by a distance greater than the distance between the given points. Now assume that we first draw a circle by placing the pivot leg at point 1 and extending the drawing leg far enough so that both given points are enclosed within the circle. Without changing the compass leg separation, this time we place the pivot leg carefully at point 2 and draw another circle. Obviously, these two circles should intersect at 2 points. Then we connect the intersection points of both circles using a straightedge. As can be seen, the straight line that connects the intersection points of both circles intersects with the straight line that joins the given points. The intersection point of these two straight lines is the desired midpoint. Now consider separating the compass legs exactly by the distance between the two given points. This time, only the center point is inside the circle, whereas the other point lies exactly on the circumference. However, as in case 1, we will have a pair of intersecting circles that meet at 2 points. Note that the intersection points of the circles lie on the straight line from case 1, therefore if these two intersection points are joined with a straight edge, again, the midpoint is obtained as desired. What if the compass leg separation is less than the distance between the two given points? Obviously, any circle drawn with the pivot leg at either of the two given points will contain only the center point. The other point will definitely be outside the circle. However, in this case, there are 3 different scenarios. In the first scenario, we adjust the compass leg separation in such a way that when 2 circles are drawn, the circles still intersect at 2 different points. As we can guess, this scenario is equivalent to the previous cases, so we will still be able to locate the midpoint by joining the 2 intersection points of the circles. In the second scenario, something interesting might occur. It is possible, though very unlikely, that the compass leg separation is adjusted in such a way that when 2 circles are drawn, the circles do not intersect but only touch each other. As everybody would agree, the point of contact should be the midpoint. However, considering practical applications, it is almost surely impossible to adjust the compass leg separation that way. Therefore, even though geometrically this is a solution, it is statistically unrealistic. So we skip to the third and final scenario. In the third scenario, the compass leg separation is adjusted so that when 2 circles are drawn, the circles neither intersect nor touch each other. They're totally separated. So there seems to be, as in the previous scenario, no immediate solution. But we need to be cautious about drawing premature conclusions, so let us investigate all 3 sub-scenarios under this third case, one by one, to see what is happening exactly. In the first sub-scenario, we adjust the compass leg separation in such a way that when 2 circles are drawn, the circles still intersect at 2 different points. Following the procedure applied in previous cases, joining the 2 intersection points of the circles will cause the line to cross the straight line that joins the 2 given points at the midpoint. So it is clear that this sub-scenario will still locate the midpoint of the given points. In the second sub-scenario, the circles do not intersect with each other, but happen to touch each other. Even though everybody feels that the point where the circles touch should be the solution, we must not forget that in order to locate a point in compass straightedge constructions, we need to intersect lines or circles. Therefore, we need to find a procedure to guarantee that we can locate the midpoint under any scenario. We will revisit this part after looking at the next sub-scenario. In the third sub-scenario, the circles neither intersect nor touch each other. They're totally separated. So there seems to be, as in the previous scenario, no immediate solution. Considering our initial constraint, that is, the use of a fixed compass leg separation throughout the process, and looking at all cases and scenarios, we can conclude that we need to have an initial guess about the location of the midpoint. This way, we can extend the legs wider than this distance, which will enable us to draw 2 intersecting circles in any case. Of course, one might reasonably argue that we can extend the legs of our compass as wide as the distance between the given points, which automatically eliminates the guesswork we mentioned a moment ago. Clearly, this gives us the midpoint in a single shot. However, this might not be feasible all the time, since the distance between the given points might be greater than the maximum leg separation allowed by the compass. Therefore, we need an algorithm that works for any 2 points with any compass. That is why our initial constraint is an obligation rather than a preference.
Here comes the Archimedean principle, where number theory meets geometry. Let us go back to the no solution case, which is equivalent to saying that the maximum leg separation of our compass is insufficient to draw 2 intersecting circles centered at each given point on the first try. So our strategy is to move along the straight line joining the 2 given points, starting from both ends to meet somewhere in between with the guidance of the compass. Just to make labeling easier, let's call the starting point P1 and the other point P2. We'll call the straight line joining them the path. Step 1. We draw a circle centered at P1 and let the drawing leg of the compass intersect with the path. We mark that intersection on the path as L1. Step 2. This time, we draw a circle centered at P2 and let the drawing leg intersect with the path. We mark this new intersection point as R1. We go back to L1 and draw a circle centered there. We note that this circle intersects the path at 2 points. One is P1, which we already have. The new point is labeled L2. Step 4. We go to the other side and draw a circle centered at R1. As in Step 3, this circle intersects the path at 2 points. One is P2. The new point is labeled R2. By repeating this process iteratively a sufficiently large number of times, we can progressively cover the entire path. As we discussed previously, the path is covered in 2 possible ways. First, the path may be covered in such a way that at some future iteration, a point Ln ends up closer to P2 than the corresponding point Rn is to P2. Or symmetrically, Rn gets closer to P1 than Ln is to P1. This guarantees that we can draw 2 intersecting circles, and therefore the midpoint can be located using a straightedge to join their 2 intersection points. In the second way, there might be a case where at a certain iteration, Ln and Rn coincide. This is equivalent to scenario B, if you recall, where the compass leg separation is perfectly aligned so that the nth iteration creates a pair of tangential circles rather than intersecting ones. So, what is the point of this algorithm? Why bother? The answer lies in the Archimedean principle. If this possible but extremely unlikely case happens, the algorithm provides a critical verification recipe. If Ln and Rn meet, it automatically implies that Rn plus 1 and Ln minus 1 should also meet, as well as Ln plus 1 and Rn minus 1, and so on. So even if Ln and Rn are so close that one might think they coincide, we carry on the procedure for further iterations. We can then verify if all the Ln plus m and Rn minus m pairs meet as predicted. If they don't actually coincide, it will become apparent as the iterations progress, revealing a mismatch between these pairs.
In this video, we've conducted an extensive analysis of how to find the midpoint between 2 points in the Euclidean plane using only a compass and a straightedge. A key part of our exploration was a self-imposed restriction, using a fixed compass width throughout the entire process. This constraint naturally led us to the powerful Archimedean principle and the fascinating world of ordered fields. In our upcoming content, we will build on this very algorithm. We'll use it to approximate the square root of 2 with rational numbers, and from there, begin to construct a rigorous foundation for the real number system. Thank you for joining us on this incredible journey through the mathematics of our universe. If you enjoyed unraveling this mystery, please hit that like button and subscribe for more deep dives into the hidden math that shapes our world. Stay tuned as we continue to explore the cosmos of knowledge, one frame at a time. Until next time, keep questioning.